So now, since we talked about RDF and we said, oh, this is large, we really have to see how large is this. Okay, large is just in the saying, or just because I want to get more grants, or is it really that there are real large data sets? So the big thing in linked data and linked open data is that because it has really seen as a bag of edges, right? That's basically what we said. Now you can throw in any kind of edge on it, right? You can just keep putting, you don't have a constraint on schema, you don't have to follow some structure. The least that you need is subject, some label on the edge, and the target. That's basically all you want. So given that, you can go across various domains, starting from biology to movies, right? And in fact, you do go from biology to movies. You look at it, the kind of LOD, that is Linked Open Data Consortium, what it is trying to do is look for such different linked data sources from different domains, put them all together, link them up, right? You may have a situation where one of the actors happened to write a PubMed article. It's perfectly possible, although very rare. You want to link this up, okay? You want to link up if there is a politician who is a chemical scientist, chemistry scientist, and has written many journal papers. You may want to know this, right?
There are huge construction issues at that level.
Construction issues at that level, right? So at this moment, what people are trying is that they are not really worried about. So there are two kinds of construction issues. You are right. One is from, you have these textual sources where people mostly report things, and you want to move from there to this kind of structure. That's one kind of structural construction issues that people are facing. In fact, Yago, DBpedia, Freebase, and TextRunner, Cyc, these are all the efforts which are moved towards focused on that aspect where you have text and you want to extract into some structured form. But what this LOD is really all about is that not really care about how they have been derived, but to put them together.
In that space only what I am saying, suppose you use TextRunner, you get something like a subject which is quite complex, like X, friend of Y, did something for something.
Yes.
So the subject is X, friend of Y, did something, part is predicate, and this. Now that X is the entity which you want to link to somewhere else.
Precisely. Yes.
So even after extraction,
yeah,
there is a problem.
Yeah. So that's the second kind of construction problem I was talking about. So in fact, even the example that you gave is already a complex one. I can take a much simpler example. So somebody is called in PubMed Mr. Howard, right? H. Howard. Okay, his name is H. Howard. And now there is another guy in IMDb which is Harvey Howard. How do I know this Harvey Howard and H. Howard, whether they are the same, whether they are different? I have no idea, right? So there is a requirement that every such entity, whether it's a node or an edge, has to be uniquely identified. So that's the basis of the way semantic web can function. That's the way LOD can function. But how do I get and assign such a unique identifier? How do I know that these two are the same? So I shouldn't just give separate identifiers. So that's a huge problem. And yeah.
Google Knowledge Base use the Wikipedia category hierarchy to identify such kind of ambiguous names.
No, Google Knowledge Base does much simpler solution for this. It minimizes the number of resources from where they take, right? And they use some standard machine learning techniques to do a relatively easy matching, right? At this moment at least, okay? And there is huge amount of human curation also going on. In fact, I was just talking about even,
They use Wikipedia category.
yeah. In fact, many of these sources, right? The yellow things that I have here. Yeah, okay. So the Yago, Freebase and DBpedia, all of them are largely built on Wikipedia. In fact, they haven't existed. If Wikipedia did not exist in such a rich form, then you wouldn't have many of these resources. But LOD is beyond just these, right? Not just the things that have come from Wikipedia, but way beyond it, because there is a whole bunch of biological facts, DBLP, citation graphs. These are not part of Wikipedia. These have come from different sources. Yes, that's what I was about to tell him, that although Google Knowledge Base, Knowledge Graph does so many things nicely, it can trip up quite badly because of exactly this problem. So I was giving an example of Rakesh Agrawal. You fire in the query, all of you can go back and try it out. You fire the query for Rakesh Agrawal, right? He is one of the well-known figures in computer science in database world. So you look at the kind of snippet that you get on the right side, which is powered by Knowledge Graph. It's perfectly matching what you know of knowledge, Rakesh Agrawal. But you look at the picture that is associated with it, it's someone else. He's from chemistry. He's also called Rakesh Agrawal. In fact, if he doesn't look like Rakesh Agrawal at all, right? So there is no, I mean, how do you believe that everything that you get is perfect, right? They try their best. So there are still, these are the research challenges which are still open, and there are many such research challenges.
Prove to anybody that entity resolution is not a solved problem.
It is not at all a solved problem. No. Entity resolution, people know that entity resolution is not a solved problem in noisy text. Like Twitter, yeah, sure, we don't know. But I'm talking about perfectly well handcrafted source like Wikipedia. Even there, things are not easy, extremely messy. Okay, so that's only one part of the problem that you will face when you go to linked open data world. And the size of the linked open data at this moment with all these errors in is about 30 billion edges. Okay, fairly large. Just compare it with something like what Facebook already announced, 1 billion users. 1 billion is already very exciting for many people, and this is 30 billion triples with so much of noise already, and clearly all these 1 billion have to be part of such a graph, right? Every human being in principle can be part of the LOD, right? So we have a
ontology here, right? I mean, what the, when any scheme, there is no superimposed schema on any of them.
there is no superimposed schema, but most of these ontologies are already part of LOD.
So, I mean, is there, so the effort of merging these ontologies together?
What do you mean by that?
I mean, for example, I mean, as you said, that there can be, people can write any predicate they want, right? So, I mean, some like Wiki taxonomy might use some different set of predicates for referring to same predicate is being used in some other, some other linked open data set.
Yes.
So merging of these two predicates, these two actual predicates are the same ones.
Yeah.
So these things, I mean,
Another research problem. Another research problem, right?
Merging ontologies.
Yeah.
Google is one which actually tried to
Yeah.
do that to give you those merged ontologies, but that's
Yeah,
a research problem.
that's another research problem which is not yet solved. Again, these things have to be solved in order to make LOD even more valuable, right? So in fact, none of this I'm going to cover in this talk at all, but I'm going to keep agreeing with all these problems that you say, yes, these are all the research problems, right?
You have to move on.
Yeah, we'll move on, right? So clearly one of the big challenges is that graphs are really big, okay? Big, massive, really massive. You can add any kind of these fancy adjectives. And more importantly, just having the graphs getting larger, the queries that you fire on these graphs are getting more and more interesting and exciting and harder to evaluate. So one is, you can have the standard pattern like queries, which you can, all of you, I think some of you already said, it's similar to SQL with few joins. Yeah, SQL has joined, really done well for join queries. But you can actually go into a little more complicated things in these graphs and say, I want to do recursive traversals with unbounded recursion, right? I just want to keep doing reachabilities, right? Then I have no good solution which is really efficient, right? This is allowed in SPARQL extensions people are talking about. And then you have on these graphs many analytic queries that you can, I mean, all of you are already familiar with PageRank. PageRank is an analytic query which runs on the entire graph, tries to rank based on their random walk potentials, right? You can also think of, I'll first fire one query, get a subgraph out, some ad hoc subset of the entire LOD, and then from this I will extract dense subgraphs or some kind of K-core decomposition of this, or compute Steiner trees, right? If you are familiar with these keyword search and graphs, this is basically what they do. They fire some initial set of queries which will filter out certain nodes and then try to connect them up using Steiner trees. Again, these are not so easy to solve using relational databases. The solution most of the current approaches use is, let's take this graph and put it in memory and deal with it. Okay. While it is a valid solution, given that the memory is getting cheaper, it's still not cheap enough to hold 30 billion triples. Okay. So we need to come up with better strategies for dealing with it.
Is there a concept of frequent item sets and rules in the world of graphs?
Yes. So you can always look at frequent subgraphs, right? So in fact, there is another, as they say, some kind of.
But now your subgraphs are not just the structure. You're looking at now at the edges also.
So you can relax the labels on the edges and say, I don't care about the edges, but really any kind of structure. Or you can say, I will include just the labels, but I relax on the subjects and objects that are there. So people have worked on these kind of
frequent subgraphs, then you can also have interesting subgraphs.
Interesting subgraphs, right?